So now I'm going to cover example 4 from lecture 4, which we did not get to in class. So the problem statement is, if we're given a vector field, which is w equal to x squared times y squared plus x, y, z, we'd like to calculate the gradient of that scalar field. Now recall from class that whenever we calculate the gradient of a scalar field, this produces a vector field. We also like to calculate the directional derivative of the vector a is equal to 3ax plus 4ay plus 12az at the point 2, -1, 0, where the directional derivative is given by the gradient of w dotted with the unit vector in the a direction. Now, as far as the directional derivative is concerned, we don't have a strong need for this in the class, but I'm just using this as an exercise to show an application of the gradient. So, what is the gradient? First, we have the definition of the gradient. In Cartesian coordinates, the gradient is defined by the partial derivative of x, the partial derivative of w with respect to x, multiplied by the ax unit vector, plus the partial derivative of w with respect to y, multiplied by the ay unit vector, plus the partial derivative of w with z, multiplied by the az unit vector. So let's calculate this equation. Let's first calculate those three partial derivatives. So the partial derivative of w with respect to x is where we would keep everything except for x constant. So y in this case is constant, and z in this case is constant, so you treat them as such. Okay, so taking the derivative of x squared would give us 2x, and then we'll multiply it by the constant, which is y squared. Here we have a first order term, so the derivative of x is just equal to 1, multiplying that by these constant here, and we have just yz. Then the partial of w with respect to y is going to give us a similar equation. So you see that we have y squared here, just like in the last example, and x is constant. So we have 2x squared y for the first term, plus, now this time the y is going to drop out because the derivative of y will be equal to 1, and we're going to have xz, okay? And then the partial of w with respect to z, we have no z in this term, so the whole term goes away because the derivative of a constant is equal to 0. We have a z here, and the derivative of the first order term is equal to 1, so all our partial with respect to z is equal to xy. Okay? So now using these, we can come up with the gradient of w, and like I said, this is in itself a vector. So we have 2x y squared plus yz. That's the partial of x. So we multiply that by the unit vector in the x direction. And then we're going to have 2x squared y plus xz. That's the partial of y, so we multiply it by the unit vector in the y direction. And then the partial of w with respect to z, we're going to multiply that by the unit vector in the z direction. So this right here is the gradient of w, and you can see that this in itself is a vector field. Okay, so the next thing is we want to get to the directional derivative in the a direction. So you'll see from the formula that we need a unit vector in the a direction. So recall that if we want to get a unit vector in the a direction, we simply take a and divide it by its magnitude. So the magnitude here, you see, we have 3, 4, and 12. So getting the magnitude of a would be 3 squared plus 4 squared plus 12 squared, square root, and that is equal to the square root. Oh, sorry, not square root. A moment to erase that. Oh, we could say square root. We could say square root of 169, which is equal to 13. Okay? So So using this, we're going to take each component of A and divide it by 13, okay? So the unit vector of A is equal to 3/13 AX plus 4/13 AY plus 12/13 AZ, okay? So now we have the unit vector for A, and we have the gradient of W. However, we want to evaluate the gradient of W for 2 for X and -1 for Y and Z for 0. So if you see where we have Z is equal to 0, this term would fall off, this term would fall off. It wouldn't affect this, but then 2 and -1, putting those in, we can evaluate, and we have, so if this is equal to 0, 2 and -1, we have 2 times 2, which is 4, and then -1 squared. So we're going to have 4 AX. And then we have 2 times 2 squared, so this is 2 times 4, which is 8. And then multiply 8 by a -1, and we're going to have -8 AY. And then here we have 2 times -1, which will give us -2. And then it's -2 AZ. Okay? So now we have the gradient evaluated at the point, and we have the unit vector of A. So we can then calculate the directional derivative by simply taking the dot product of the two. Okay, taking the dot product, we'll multiply the x components. So 4 times 3/13 will give us 12/13. Right? Remember, dot product is a scalar. So we're then going to add that to the y components multiplied. So -8 multiplied by 4/13. That's going to be -32/13. And then we're going to multiply a -2 with 12/13, and that's going to give us -24/13, and that will give us our final answer, which is -44/13.